Well, hello and welcome. And we are here to solve yet another, in fact, problem from calculus. And the problem says that it's a very interesting one, quite as old as a tale. The problem says that you have to prove that for every odd degree polynomial with real coefficients, it must have a real zero. Something that we can always do using hand waving approach. And we can say that, well, this will happen, and therefore that will happen, and therefore it must have a real root. But in this session, at least, we are interested in proving this article rigorously. So assume that the polynomial is, say, p of x is something like x to the n plus an minus 1 x to the n minus 1 plus an minus 2 x to the n minus 2 and so on all the way plus a1x plus a naught where n is odd. Right. And if p of x is if this form and where n is odd, then what we're supposed to do is that we're supposed to prove that this polynomial must have at least one real zero, given that the coefficients are all real. Look, the fundamental point behind doing all of this is that we have to somehow show that there does exist some value of x for which this polynomial almost behaves like x to the n. So if you think about it, that if x is sufficiently large, although the word sufficiently is vague, then this function is as great as x to the power n, right? So what we're going to do is that, well, a p of x can be thought of as x to the n into 1 plus an minus 1 upon x plus an minus 2 upon x squared and so on in naught upon x to the n, right? So what we are trying to do here is that we are trying to find a nice and large values of x, nice and large value of x for which this quantity almost vanishes so that this function behaves like x to the n. Can we find that quantity? Well, here is the thing, and this is the part that you have to sort of think about it. How did it come into being? So I say that take mod of x to be greater than the maximum of these quantities. Now, which quantity is 1, 2n times an minus 1, 2n times an minus 2, and so on, so on, so on. 2n times a naught. So mod of x is greater than greater of these numbers, which means that mod of x is greater than all of these numbers individually. Right. So have a look at these numbers. So you can think of mod of an upon x plus an minus 2 upon x squared and so on in naught upon x to the n. And by triangles inequality, we can agree that this is less than or equal to, in fact, mod of an minus 1 upon x plus mod of n minus 2 upon x squared, so on, plus mod of this, right? Yeah, they're simply triangles inequality. So I'm just going to copy the conditions that for what values of x are we interested in. So we are interested in these values of x. Right, so have a look at this. Since x is essentially greater than, mod of x is essentially greater than 1, we can say that this quantity is further smaller than mod of an minus 1 upon mod of x plus mod of an minus 2 upon mod of x and plus all the way up to mod of a naught upon mod of x. Convince yourself that this is the case. And why is this the case? Because if mod of x is greater than 1, then mod of x to the power n for n greater than 1 is greater than mod of x. And therefore, this is going to be true, right? Okay. So now what I'm going to do is that, now think about mod of x. Since mod of x is in fact greater than 2n times an minus 1, So this means that this number is less than 1 by 2n, precisely less than 1 by 2n. Now, since mod of x is in fact greater than 2n times n minus 2, so this number is also precisely less than 1 by 2n and 1 by 2n and so on all the way to 1 by 2n. Right, so how many 1 by 2n's are we dealing with? We are dealing with n 1 by 2n. So this begins with naught, goes up to n minus 1. So there are n 1 by 2n. So if there are n 1 by 2n, so they all add up to 1 by 2. Which means that what we've essentially proved is that if you were to take x, mod of x, in fact, satisfying these criteria, so what you essentially get is that mod of an minus 1 upon x plus mod of an minus 2 upon x square and so on. This is essentially less than 1 by 2, which means that this number, an minus 1 upon x, an minus 2 upon x square, and so on, lies between minus 1 by 2 to 1 by 2. Are we clear? So which essentially means that the number px, I remember px was something like that. So in fact, it's 1 plus an minus an by x power n. So essentially, if you are going to choose your x in this region, then what we have proved that this number lies between minus 1 by 2 to 1 by 2, which essentially means that this number lies between 1 by 2 to 3 by 2, right? So this number will lie between 1 by 2 and 3 by 2. So if this number indeed lies between 1 by 2 and 3 by 2, then it means that this number is indeed positive. And if this number is indeed positive, then find an x1 which is positive and which satisfies this criteria. Now, if you find an x1 which is positive and which satisfies this criteria, then obviously p of x1 is going to be positive. Why? Because this number is positive, x1 is positive, n is odd, so that's that true, right? And similarly, you can find an x2 which is negative and which satisfies the same criteria, that for which mod of x2 will be greater than maximum of these numbers. In that case, again, this number is positive, x2 is negative, n is odd, so this quantity becomes negative, so p of x2 is negative. And since p is continuous, because p is a polynomial, so therefore there does exist some x between x2 and x1 for which p of x must be 0 by intermediate value theorem. And therefore, every odd degree polynomial will have at least one root, right? And we're done.